So for each of these, let's get some practice of finding those critical points, and then we're going to go looking for local extrema, minima and maxima. And what we can do is use the first or second derivative test. It's up to us which we want to use. So I'll just kind of switch between the two so you can see both processes, but it really will accomplish the same thing between the two. It's just kind of like if you like to use increasing, decreasing versus concavity to recognize minimums and maximums. Okay, so this first one. So we're going to start with our critical points. And with that, we're going to take our first derivative, which will be x squared minus 5x plus 4. And what we want to do is see where that's equal to 0. And this will be factorable, so that'd be very nice with x minus 1 times x minus 4 to give us x equals positive 1, x equals positive 4. So there's our two critical points. Now what we want to do is evaluate whether it's a minimum or a maximum or neither at these points. As we saw with some examples, these could just be an inflection point, so we want to be careful of that. I'm going to go ahead and do the second derivative test with this one, just because the second derivative is pretty nice here. So that's going to be my second step. I'm going to look at the second derivative of our function, which will be a 2x minus 5. And what I'm going to do is I'm going to evaluate the second derivative at each of these points. And all I care about is whether it's positive or negative. So let's see, 2 minus 5 is a negative 3. So that's negative, and that tells me that at that value we are concave down, which means we have a shape like this, which means we're making a local maximum. And then our second derivative of positive 4 will be at 8 minus 5, so a positive 3. So this is concave up, which creates this shape right here, which means we're making a local minimum. I'm going to double check the wording to see. We want to find critical points. Let's go ahead and get the xy coordinates, just because I believe so far we've only really found the x values. Not that finding the y values is difficult, it just requires plugging into our function up above. So we have a local maximum at the coordinate 1, and then we'll have, let's see, a third minus 5 halves plus 4. When we plug in a positive 1 for x. And let's see, that'll be a 2, 6 minus 15, 6 plus 24, 6. Okay, so a negative 13 plus 24 for 11. And I did that mental math pretty quickly there, so I'm just going to check it in my calculator real quick. That was some fast fraction math, and, well, it wasn't terribly fast, but I just going to double check that 11/6. Yay! Okay, so that's our local maximum, and then we have a local minimum at, and if we plug in 4, I'm just going to go ahead and throw all this into the calculator. So 1/3 times 4 cubed minus 5 halves times 4 squared plus 4 times 4 for a negative 8/3. Okay, so this was using the second derivative, so finding those critical points. Then evaluate concavity, or the second derivative, at each of those values, and that'll tell you whether it's making a maximum or minimum. Let's do this next one, and how about this one? I'll do the first derivative so that we can see the two next to each other. Okay, so first I want to look at critical points. So I'm going to take the first derivative, which is a 3 times x squared minus 1 squared times 2x with our chain rule. I'm just going to rearrange that a little bit, and we're solving for where this is equal to 0. So we have 6x times x squared minus 1 quantity squared. And with that, we're going to have 6x equals 0. And let's even separate this up. And x squared minus 1 equals 0. So this will give us x equals 0, and then x squared equals positive 1. Take the square root of both sides, and we're going to end up with a positive 1 or a negative 1. So you end up with 3 critical points here. Now what we're going to do is set up our intervals, like the first derivative test, because that'll show us what's happening to the left and right of each of these values. So we're going from negative infinity to negative 1 is our lowest value, negative 1 to positive 1, 1 to 0. Nope, that's not how numbers work. Negative 1 to 0. This is why I like my little number line thing. So I can see them all in order and see all the intervals we're going to have come through. So 0 to 1, 1 to infinity. And what we're going to do is evaluate a first derivative in each of those intervals. Have a negative half, positive half, and a positive 2. And we're plugging that into the 6x times x squared minus 1. So we'll have a negative 12 times 4 minus 1 squared. So that'll be a negative value. So that tells me that we are decreasing there. And this is where we have our critical point, x equals negative 1. And then to the right of it, if we plug in a negative 1/2, so let's see, that'll be a negative 3 times 1/4 minus 1 squared. And that is negative as well, so we are decreasing. And then a positive 1/2. And that will be positive 3 times 1/4 minus 1 squared. And that's going to be positive. So we are increasing. And then a positive 2 will also mean we're increasing. Okay, and here's our x equals 0, x equals positive 1. So what we're seeing is we're decreasing, then we're decreasing again. So what I'm thinking is there we're seeing that kind of flattening of an inflection point. And we could confirm that with the second derivative, but that's what we're seeing when it's matching up. Whereas when we're decreasing to increasing, so I'm seeing a minimum come through. If we're going down and then up, that'll create a minimum. And then we're increasing and increasing, so I'm expecting something like that there. So even with that, I can start to get a shape for the graph of that we're decreasing, we hit a minimum, increasing, increasing, something like that. And then let's also go to Desmos to check it out, because especially with these, I have different scenarios, it's nice to really confirm with the graph. So we have x squared minus 1 quantity cubed, and there it is. There's the shape of our graph. So we're getting those inflection points that are not creating a minimum or a maximum, and then we're seeing this minimum at 0, negative 1. So our only extremum is a local minimum at 0, and then negative 1 cubed, so negative 1 would be our y-coordinate. Okay, one more example here with a rational function. So let's start with our critical points. And with that, our first derivative is going to be low d high, so 1 plus x squared times 4 minus 4x times 2x all over 1 plus x squared squared. And something I'm going to notice here is with this denominator, also want to pay it to, actually, you know what? Nope, we don't have any vertical asymptotes coming through. I was going to say we want to look at where this is undefined, but we should be able to plug in anything for x right there. We won't be able to get a 0 out because of that square. Okay, so we're good there. Okay, first derivative, so we're going to have a 4 plus x squared minus 8x squared over 1 plus x squared quantity squared. And I left a 4 off there from distributing. Okay, so we're looking for where 0 equals a negative 4x squared plus 4 over 1 plus x squared squared. And if we multiply both sides by that denominator, we're really just looking for where 0 equals negative 4x squared plus 4, which is 4x squared equals 4, which is x squared equals 1. And taking the square root of both sides, we'll get x equals positive 1, x equals negative 1. Now, I could go ahead with the second derivative. I don't really want to do quotient rule again. It's not terrible. But I'm going to go with the first derivative test with this one, just so I don't have to take the derivative again. It might be that we have to confirm some information, but just while we're here, let's stick with the first derivative. So I'm going to go negative infinity to negative 1, negative 1 to positive 1, and then 1 to infinity. And then I want to evaluate a first derivative in each of these intervals. So how about a negative 2, a 0, and a positive 2? And we'll plug that in. So if I plug in negative 2, let's see, that'll be a positive 4. So I'll make a negative numerator. And no matter what, the denominator is going to be positive because of that exponent of 2. So the numerators will be negative, so that'll make the overall value negative. So we're decreasing. If I plug in 0, that would be a 0 plus 4, so that'll be positive. And if I plug in positive 2, that'll be a negative 4 times 4, so negative 16 plus 4 is negative. So we're decreasing. So we're going down and then up and then down. And here's our critical value of negative 1. Here's our critical value of positive 1. So if we're going down and then up, that's making a local minimum. If we're going up and then down, that's creating a local maximum. So we have a local minimum at the coordinate negative 1, and then if we plug in negative 1, let's see, there'll be a negative 4 over 2, so negative 2. And then a local maximum at positive 1, which will be 4 divided by 2, positive 2. And again, with these, while you're working on your assignments, you can check with Desmos by graphing. So we could go 4x divided by 1 plus x squared. And looking at our graph, here we can see maximum 1, 2, minimum negative 1, negative 2. So Desmos highlights those coordinates really nicely as kind of special values. And with that, we could double check that we have the same thing. Okay, so you can use first derivatives or second derivatives. Personally, my routine is I use the second derivative if it's nice to take the second derivative, if it isn't too much extra work, or like in this case, it even makes it simpler to plug in things. But with more complicated scenarios, it's kind of nice to use the first derivatives for simplicity.